안녕하세요. 오늘 우리는 연구원입니다. Today we are going to be researchers. So what I want to know with this Indramat motor, if I ever had to change the feedback, because it's a feedback that's timed to the windings of the motor. If there was a way that I could replace that feedback and get it properly timed to the windings of the motor. So we're going to try and figure out a way to do that today. We're going into unknown territory. So here's our bus power supply and Indramat servo drive. And I have communications from the servo drive to the laptop here. And when you power up that servo drive, it actually emits data from the servo drive to the laptop. And we're going to use HyperTerminal to view that data. Let's go ahead and power up the system and make sure we have a good encoder and good motor before we do anything. Okay, the drives come up to AB in the 7-segment display, and we're going to connect the RF terminal to plus 24 volts DC. Okay, the brake has been released. There's an electromechanical brake inside this motor. The drive releases that brake when you connect the RF terminal to plus 24 volts. Now we're going to connect the AH terminal to plus 24 volts. And we're moving. We have a good system here. Now, we're going to bring up the Hyper Terminal program and we're going to look at the data that's being emitted from that drive. Okay, let's click on Hyper Terminal. We'll cancel here and we'll go to Open and we'll click Indramat number 2. This has the HyperTerminal parameters to communicate with that drive. And here it says to start parameterization and diagnostics program, press enter. Press the enter key and here's the main menu. If we press the number 1 key, we'll get drive status. Let's go look at that. Okay, the drive is enabled. We're running a motor. And down here, we have angular degrees and rotor position revolutions. We're going to try to use that to time, to establish the timing of that encoder to the windings of that motor. Let's get back out of here. I'm going to press the escape key. Can y'all see that okay? Do we need to get closer? Let's get closer to that Hyper Terminal. There we are. We're a little bit closer. So let's press the escape key. And we'll go to drive parameters, pressing the number 2 key. Now down here it says, we've read the warning. It says don't be stupid. No, it don't say that. It says just be careful when we're making changes with the gain parameters because the drive can become unstable when running that motor if we apply the wrong gain parameters. But we're not going to mess with the gains. So we press the C key, and here's some of the stuff that we can look at. Operational mode scaling, encoder emulation setup, error reaction, torque limits. There's the gain parameters. We're not going to go in there and mess with those. And motor and drive data. Let's go look at the motor and drive data real quick. Here's the drive. It's a DDS 3.1-W050-D. -D indicates that it uses digital feedback. If you see a -R, it uses resolver feedback. Here's the MDD071B. That's our motor. Let's get back out of here. Let's go look at item 9, feedback and amplifier data. Let's see what's in there. Okay, it says right here, in this menu, you get an overview about the internal data stored in feedback and amplifier by Indramat. There is no possibility to edit them. The important one here for us, because we're going to lock the rotor in positions until and view that angular position parameter with the laptop. So here, number of pairs of poles is 3. This is a 6-pole motor, 3-pole pairs. So when we lock the rotor, it will lock in 3 different positions. So for instance, if we lock the rotor using U and V windings, we will be able to lock that rotor in 3 different rotational positions throughout the 360 degrees. We'll do that here in just a little bit. Let's get back out of here. And let's go back up to number 1. There's number 1. Okay, let's go look at number 2. That's the encoder emulation setup. This is the one where we're going to look at the angular position in degrees. So as we rotate that shaft, this changes from 0 degrees to 360 degrees. At some point, I believe, hopefully, we'll be able to lock that rotor either UV, UW, or VW and see either 360 degrees or very close to it, or 0 degrees or very close to it. Our screen just went wonky. My feedback cable is not shielded. We're picking up a lot of electrical noise, and it gets injected onto the communications line. Let's back out of here. Let's go look at 3. 3 is what happens when we have an error. Right now it's set to 0, and 0 says that the drive automatically switches to velocity loop regulation and provides a velocity command value of 0 after 500 milliseconds. The motor torque is disabled and an error signal is sent to the power supply on the X1. It looks like X1.2 connector. I wonder if that's X1 pin 2. So right now it's set to 0. Let's get out. We'll go look at item 4, torque current limits. Okay. Let's go look at the gain parameters. Right now, current loop proportional gain is set to 10. Velocity loop proportional gain is set to 500. Smoothing time constant, 400 microseconds. Velocity loop integral reaction time in milliseconds is 8. And we can change those. We'd have to stop the drive and disable the output before we made these changes. But this was the one where we had to be careful making changes because that motor can bounce all over the place if we don't put the right value in here. Okay, hit the escape key again. We already saw item 6. Item 7 is save and load parameters. And 9, that was your feedback and amplifier data. So this motor has a brake. And what we're going to have to do is we're going to have to get a power supply. When we lock the rotor, we're going to have to get a power supply to also release that brake. Right now, the brake is released from the drive. Okay. Disable the drive from running. Disable the output. Here's the brake engage, and I can't rotate that motor. We're going to power down. Now, I'm going to disconnect U, V, and W of the motor. Now here's the red wire, black wire, blue wire, frame ground. Okay, the brake is the middle pin and the bottom pin. Okay. Writing this down so I can get them hooked up again. Okay, I'm going to have to disengage that brake with a separate power supply. Okay, let me find another power supply. I'll be right back. Okay, now I have this power supply here, positive, connected to A1 on the motor and A2. Now let's power up the drive. We're going to lock the rotor with this power supply. I got it set to 3 volts, about 3.3 volts DC. So let's turn this on. Now you can see that the shaft moved a little bit and it's locked. Now I have the brake released with the power supply up there, 24 volts DC going to the brake. Now we're going to go over and look at the laptop and see our angular degree is. At that point right there it says 209.9676 degrees. We'll come back to that in a little bit. Let's turn the power supply off. Now remember we said this is a 6-pole motor. There'll be 3 places where it will lock in. There's the second place. And the angular degrees is 330.7825 degrees. Turn the power supply off so we can rotate the shaft. And there's the third position. And we have, this is interesting, at that point right there, we have 90.6293 degrees on the laptop. The data coming from the drive. Now let's see if we can lock back into the first position we were at. And there we're at 210.5715 degrees. Try it again. There's 331.050 degrees. And let's see if we lock in at 90 degrees again. Right there, we're at 90.5507 degrees. That 90 degrees is an interesting number to me. So, let's get over in front of the laptop and we'll document these angular degree positions as we lock that motor in its 3 positions. Then we'll move from A1 and A2 to A1 and A3 due to the 3 locked rotor positions. And then we'll move from A2 to A3 and the 3 locked rotor positions. Now we're going to write all this down. I have a chart. Let me show this to you. I'll put this up at the end of the video. But right here, these are the pinouts of the motor. And here's the chart that we're going to document our 3 locked rotor angular degrees. There's A1 to A2, A1 to A3, and A1 to A2. I'm sorry, A2 to A3. Okay, I have positive 3 volts applied to A1 and ground of that power supply connected to A2, and we're locked in the first position, and I'm going to document this. That's what, let me pull up a chair. Just a sec. I'll get there. Old man's kind of slow today. So we have an angular degree 210, let me write that down, 210.59, we'll say 5962. Okay, I'm turning off the power supply that's locking the rotor to A1 and A2. I'm rotating the encoder just a little bit, turning on the power supply again. We move to the second position and we have 330 degrees, 330.4392. Alright, turning off the power supply. I'm going to move the shaft of the motor by hand just a little bit. Now we're locked in again by turning on the power supply. And there's our 90 degrees. 90.5692 degrees. Okay, turning off the power supply that's locking the rotor. Now I'm going to move A2 to A3. So we're going to be applying 3 volts to A1 and A3. So here's A2 to the A3 pin. Get in there and see. There we go. Okay, turning on the power supply to apply plus 3 volts to A1 and ground to A3. Let's see what we have. We have 111.282. Let's write that down. 111.0316. Okay, degrees. Okay, turning off the power supply, rotating the shaft of the motor just a little bit so we can lock it into that second position. And let's see what we have. power supply has been turned on. We've moved to the second position, 230. I'm writing all this down as we go. 5512 degrees. 230.5512 degrees. Turning off the power supply, that's locking the rotor, rotating the shaft a little bit. There we're locked into the third position. 351.2357. 351.2357 degrees. Okay. Now we're going to move A1 to A2. The power supply is turned off, and I've moved plus 3 volts from the power supply connection to the A2 pin with the ground on A3. Let's see where we go. We move to the first position. There's 11.3375. Okay, 11.3375 degrees. Turning off the power supply, moving the shaft a little bit so we can lock into the second position. Turning on the power supply, there's our second position. We have 130.8798. 130.8798 degrees. Okay, powering down the power supply, moving to the last position. Turning on the power supply. Let's see where we're at here. 250.8433. 250.8433 degrees. The only one that stood out with, in my mind was that one where we were 90.57 degrees, 90.5692 degrees. That was the closest one that I could see. So theoretically, and I'm not going to prove it because I don't want to tear up my motor, but if we had to replace that encoder, we could lock the rotor and rotate the encoder until we had that 90-degree point. So we could apply positive 3 volts to A1, ground to A2, rotate the encoder until we had that timing of 90.5692 degrees. Theoretically. Now, if y'all ever have to change out an encoder, let me know if this works. Let me turn off that power supply, locking that rotor. Okay, I think we're done. I'm going to look around this program a little bit more and see if there's anything else that could help us time that encoder. Let's go look around and see if we can find anything else that could help us time that encoder to the windings of that motor. Let's see, this is option 1, operation modes and scaling. Yep, I don't see anything there. Let's go to number 2, encoder emulation setup. This is where we saw our angular degrees that we were just using. Error reaction, there's nothing there to do with feedback. That's option 3. Option 4, torque current limits, there's nothing there. The gain parameters, option 5, nothing to do with feedback there. Per se, that would help us to time that encoder to the windings of that motor. Let's go to motor and drive data, see what we have there. That's option 6. I don't see anything there. Okay, let's get out of here. Option in 7 and 8, that's save and load parameter. Let's go look at option 9. Now we can't change these values, but maybe there's something here that we could use in addition to the data that we just gathered. Let's see, there's current loop proportional gain, velocity loop proportional gain, velocity loop integral reaction, smoothing time constant, number of pole pairs, that was important, 3 pole pairs, 6 pole motor, holding bright current, feedback type, number 4, encoder count 512. It's probably 512 pulses per revolution. Key slot angle 0.0. That's the keyway on the motor. So when that motor's at 0.0 degrees, that keyway should be at whatever position they're calling 0. Now this is interesting. Commutation offset 248. And the feedback interface is 3. I'm not sure what all those values are, but they have something to do with the feedback. Interesting. Okay. All right, all. Thank you very much for coming by and helping me research that problem right there. Now, I wouldn't recommend y'all take that feedback device off of your motor unless you absolutely had to. For instance, if you had to pull the rotor to have it rewound, of course you're going to have to take that feedback off. But if you've got a good motor, don't separate the two, because it would be a lot of fun trying to put that back together properly timed. And if you didn't have a drive and a bus power supply and the cabling, it would be near impossible, because you have to be able to verify your position is correct by running that motor. So don't do it unless you absolutely have to. And if you do, let us know in the comment section whether you were successful, or if you have a different way of performing that reinstallation of the encoder, or replacing a bad encoder with a good encoder. Let us know how y'all do it. This is just the old man thinking outside the box. Okay. All right. Anahi. Que sei eu.